In this video, we will be looking at section 3.3, which covers graphs of polynomial functions. We're going to start by finding intercepts. It says given the function p of r equals 3r to the fourth minus 3r cubed minus 18r squared, find the p and r intercepts. Now I know these are different variables than we're used to working with, so let's see if we can put these into terms that might make more sense to us. Notice that the r is our input value. It's in place of where x normally is. That means p, which is on the other side, represents what y normally does. Well, to find a y-intercept, or in this case a p-intercept, we let the other variable, typically x, but in this case r, be equal to 0. So if we let r be equal to 0, we get p of 0 is equal to 3 times 0 to the fourth minus 3 times 0 cubed minus 18 times 0 squared. That's just 0. So we know when r equals 0, p equals 0. Now we need to find our r-intercepts. To find r-intercepts, we let p be equal to 0. That'll give us 0 is equal to 3r to the fourth minus 3r cubed minus 18r squared. But we don't have a formula for how to solve polynomials that are raised to the fourth power, so let's think about what else we have as tools to help us solve this. Well, we can always factor out a greatest common factor if we have one. Let's try that. That'll give us 0 equals 3, 3, and 18. I can factor 3 out of that. R to the fourth, r cubed, r squared. I can factor out an r squared from that. That will leave me with r squared minus r minus 6. So I have my term out front. Now I need to deal with this guy, r squared minus r minus 6. That factors 2, but not with a greatest common factor. R squared minus r minus 6 factors into two binomials. With r's out front, we're going to have a minus 3 and a plus 2. So now that it's all factored out, I can remember that since these are all multiplied together and equal 0, one of these has to equal 0. So either 3r squared equals 0. Dividing both sides by 3, we get r squared equals 0. And the square root of both sides gives me r equals 0. If r minus 3 equals 0, then r equals a positive 3. And if r plus 2 equals 0, then r equals a negative 2. So we get if r is 0, p is 0. We get if r is 3, p is 0. And we get if r is negative 2, p is 0. Those are our three r-intercepts. We're going to go a little bit out of order because I think it makes a little more sense this way. We are going to look at the long-run behavior of polynomials. Recall for any polynomial, the long-run behavior of the polynomial will match the long-run behavior of the leading term. So we looked at this before when we had an expanded polynomial, but in this case, it's all factored. We want to see if we can still determine the long-term behavior of f of t equals negative 2t times t minus 1 squared times t plus 3 times t plus 2 cubed. Now, if you really want to multiply all those together, be my guest, but I have a feeling there's a slightly better way. I want to think about this t minus 1 squared. That means t minus 1 times t minus 1. If I were to FOIL that out, I would end up with t squared minus 2t plus 1. The leading term out of that is the t squared. All I care about right now is the leading term. So from that, I can extract a leading term of t squared. From t plus 3, the leading term is just t. From t plus 2 cubed, I can pull out a t cubed as my leading term, because I would have t plus 2 times t plus 2 times t plus 2. So the leading term is t, t, and t, gets us to t cubed. And don't forget, we have this negative 2t out front. So our leading term is going to be negative 2 times t squared times t cubed. So that's 3, 4, 5, 6, 7 factors of t. Our leading term is negative 2t to the 7th power. So we know that our odd power functions go towards negative infinity on the left and positive infinity on the right, but we have to flip it because we have a negative leading coefficient. So we are looking at something that looks like that. So as x goes towards negative infinity, our function values f of t go towards positive infinity. As x goes towards, oh sorry, we don't have x's, we have t's. As t goes towards, this time positive infinity, our function values f of t goes toward negative infinity. So we go toward positive infinity on the left and negative infinity on the right. Next up, we are going to look at graphical behavior at intercepts. On the right, you will see the graph of the function f of x equals 0.1 times x plus 2 squared times x minus 1 times x minus 4 cubed. What can you know, or what do you notice about each graph at each of the zeros? Notice about the graph at each of the zeros. Can you make any connections between the graph and the algebraic function? So we know, because this is in factored form, that we are going to have zeros, which are also known as x-intercepts, at negative 2, positive 1, and positive 4. So let's take a look at this. At x equals negative 2. I see that the function comes down and kind of bounces back. It bounces back. At x equals positive 1, the graph just kind of goes through like it normally does. At x equals 4, it does go through, but it kind of levels off at 4. So it levels out but keeps going. So what I want to do is I want to take a look at the function and see if we can make any connections as to what's going on here. Starting by looking at the term with our x plus 2, it is squared. In that case, our function bounced back. If you just look at that little section, it kind of looks like an x squared. So it looks like when our term is squared, we get this bounce back feeling like we would if we were looking at a quadratic. This middle term, x minus 1, is just raised to the first power. We went straight through, kind of like a line. In a line, we go straight through stuff. In our last term here, we're looking at x minus 4 cubed. So that's cubed raised to the third power. We got that it leveled off at our 0 and kept going on, like an x cubed graph does. So if we have a single 0, meaning our power on that term is 1, we're going to go straight through. If we have a multiplicity of 2, so if the power on that term is 2, we're going to get this bounce back behavior. If we have a 0 with multiplicity 3, so if the power on that term is 3, we're going to get this leveling off behavior and then continuing on. So what we're going to do is we're going to see if we can write an equation using intercepts. We're going to try. If a polynomial has horizontal intercepts at the x values x1, x2, all the way up to xn, then the polynomial can be written in factored form as f of x equals a times x minus x1 raised to the p1 power times x minus x2 to the p2 power of through x minus xn to the pn power, where the powers, pi, so all of these p's, those are the multiplicity. We can determine those by the behavior of the graph at the corresponding intercept. Then we can find the stretch factor a by looking at a point on the function other than the horizontal intercepts. So what we're going to do is we're going to find all of our x-intercepts, determine the multiplicity of each one, write it out in factored form with an a out front, and then we're going to use another point to solve for what a is. So it says the polynomial of degree 4 p of x has a root. I should point out, because we've used a bunch of different words now. Root means the same thing as x-intercept, which means the same thing as a 0. Not the number 0, but a 0. So p of x has a root of multiplicity 2 at x equals negative 2, and roots of multiplicity 1 at x equals 0 and x equals 1. We know it also goes through the point 3, 15. We want to find a formula for p of x. So let's start by looking at our roots, also known as our x-intercepts. We know that there is one at x equals negative 2, and it has a multiplicity of 2. What that means in my equation is that I'm going to have x minus a negative 2, and the power on that term is going to be 2 from the multiplicity. So I changed it to positive because it's x minus the root. At x equals 0, we have a multiplicity of 1. So in my formula, I'm going to have x minus 0 to the first power. So that just means x. At x equals 1, we have a multiplicity of 1. So we will have x minus 1 also to the first power, but that doesn't simplify. So when I go to make my formula for p of x, I need my a out front, and then I put in all of these factors. I'm going to put the x out front because that's normally what we do if it's not in parentheses. Then we have our x plus 2 squared and our x minus 1. Now I'm going to use the point they gave us, this 3, 15. So that'll be 15 equals a times x, which is 3, times x, which is 3 plus 2 squared, times 3 minus 1. And we're going to solve for a. So we get 15 equals a times 3 times 5 squared times 2. So that's 15 equals a times 3 times 25 times 2. So 15 is equal to 3 times 25 is 75. 75 times 2 is 150. So we get is equal to 150 times a. If I divide both sides by 150, we get a is equal to 15 over 150, which is 1/10. Now that I know my a value, I plug it back in, and my formula for p of x is going to be p of x is equal to 1/10 x times x plus 2 squared times x minus 1. That's what we got. We're going to try one more, but this time we're going to be given a graph instead of everything in words. So given the graph, we want to find a formula for this function. Let's see if we can run it the same way we did the last one, where we find our roots. So here at x equals -1, we get that bounce back feeling. So that's going to have a multiplicity of 2. Here at x equals 2, we get that level off kind of feeling. So that's going to have a multiplicity of 3. And here at x equals 4, it goes straight through. So that's going to be a multiplicity of 1. So now let's see if we can come up with our formula. We'll call this f of x. F of x is equal to a, which we'll solve for later. We have a root at x minus 1, so that'll mean I'll have x plus 1. And since it has a multiplicity of 2, it'll be squared. Then I have x minus 2, that has a multiplicity of 3, so that'll be cubed, times x minus 4, and that only has a multiplicity of 1, so that stays. Now I need a point on my graph that I haven't used yet. I kind of like this one. Looks like we go through 0, -4. So let's try plugging that in. We'll have -4 is equal to a times 0 plus 1 squared times 0 minus 2 cubed times 0 minus 4. So that means -4 equals a times 1 squared is 1. -2 cubed is -8. And 0 minus 4 is -4. So we have -4 equals 32a. When I divide both sides by 32, we get a equals a -1/8. I plug that back into my function, and our function f of x is equal to -1/8 times x plus 1 squared times x minus 2 cubed times x minus 4.